Mathematics is everywhere, from business decisions to medical advancement to environmental studies. Derivatives help us analyze change and make informed decisions. Today, we'll explore three key real life applications of derivatives: maximizing profit, drug concentration in the blood, and climate change and ice melting. So, why do derivatives matter in these real world situations? Let's find out. Every business wants to maximize profit while minimizing costs. But how can calculus help? Let's consider a company that manufactures and sells mobile phones. The total cost in pesos of producing X units is given by C of X equals 5,000 plus 200X plus 5 tenths X squared. The total revenue in pesos from selling X units is described by the function R of X equals 500X minus 3 tenths X squared. Find the number of units the company should produce to maximize the profit. To determine the profit function, we subtract the given revenue and cost equations. That is, P of X equals R of X minus C of X, where R of X represents revenue and C of X represents cost. We replace R of X and C of X with their corresponding function. Simplifying, we get P of X equals negative 5,000 plus 300X minus 8 tenths X squared. To find the maximum profit, we take the derivative of the profit function by applying the derivative rules. We get P prime of X equals 300 minus 1 and 6 tenths X. Equating the first derivative of the function to 0, we get 0 equals 300 minus 1 and 6 tenths X. Solving for X, we will have 187 and 5 tenths. We check whether the function will have its maximum value at X equals 187 and 5 tenths using the second derivative test. The second derivative test states that if the second derivative of the function is greater than 0, then the function has a relative minimum value at X equals C. If the second derivative of the function is less than 0, then the function has a relative maximum value at X equals C. Now we get the second derivative of the given function. We will have P double prime X equals negative 1 and 6 tenths. Because the second derivative is negative, we confirm that the maximum value of the function occurs at 187 and 5 tenths. Since the company cannot produce a fraction of a phone, we round 187 and 5 tenths to 188. Therefore, the company must produce 188 units to maximize the profit. Medicine is carefully dosed to ensure safety and effectiveness. One crucial factor is how quickly a drug leaves the bloodstream. This can be modeled using an exponential function. Suppose a patient is given a drug and its concentration in the bloodstream follows the equation C of T equals 50E raised to negative 0 and 2 tenths T, where C of T represents the drug concentration in milligram per liter after T hours. Find the rate at which drug concentration is decreasing after 4 hours. To determine how fast the drug level is decreasing after 4 hours, we take the derivative of the function, which is C prime of T equals negative 0 and 2 tenths times the quantity 50E raised to negative 0 and 2 tenths T. Simplify this, we will have C prime of T equals negative 10E raised to negative 0 and 2 tenths t. Substituting t equals 4 into the function, we get negative 10e raised to negative 0 and 8 tenths. Using a calculator, we find that the drug concentration is decreasing at approximately 4 and 49 milligram per liter per hour after 4 hours. Doctors use this information to determine the right dosage intervals, ensuring that the drug remains effective without overdosing the patient. Climate change is one of the most pressing issues of our time. Scientists track glacier melting using exponential decay functions. Suppose the thickness of an ice sheet in meters follows this model. H of t equals 50e raised to negative 0 and 200 t times the cosine of 1/10 t, where h of t represents ice thickness after t years. Find the rate at which the ice sheet is thinning after 10 years. To find how fast the ice melting after 10 years, we take the derivative using the product rule. Let u equals 50e raised to negative 200 t and v as the cosine of 1/10 t. We get the derivative of each expression. We will have u prime equals negative e raised to negative 0 and 200 t, and v prime equals negative 1/10 sine of 1/10 t. Injecting it to our formula, we will have h prime of t equals negative 5e raised to 0 and 200 t times sine of 1/10 t minus e raised to negative 0 and 200 t times the cosine of 1/10 t. Substituting t equals 10 and simplifying, we find that the ice melting is at a rate of 3 and 89 hundredths meters per year. These calculations help scientists predict rising sea levels and the effects of global warming. Derivatives are more than just mathematical concepts. They are essential tools in economics, healthcare, and environmental science. We've seen how they help businesses maximize profit, doctors manage drug levels, and scientists track climate change. Now, imagine the other ways calculus shapes the world around us.